Wait, starting in a minute here. Just wanted to see. I was curious, did either instructor ever talk about or cover Euler's method or Euler's method? If they might have incorrect. Okay. It's usually covered in this chapter, but that's totally fine. They didn't cover it. Want to make sure that I wasn't missing it. So I was imagining you all probably wanted to talk more about differential equations and how to solve them and how to set them up. Yeah. Lots of examples here. Here it is. Yeah, okay, sure. Yeah. So he's posted many, or Dedell has posted many examples on Canvas. I think most of them with solutions. Where are there actually homework problems on this first order linear stuff that are due? There are, okay, but where are they?
It's called it's spelled wrong. It's a PDF and it's
Okay.
differentials.
Okay, differentials. Is that in the modules?
Yeah. Differentials, and then like 4 A, B, C, D, and then 5 and 6.
Where is it in the
And handouts
handouts? Okay.
at the bottom.
Yeah. The first order linear differential equations posted for students.
Uh,
Oh no, the differential. I see.
Yeah.
Differential. Oh, okay, I see. Oh shit. So
There's just a couple at the bottom.
so it's interesting because like I'm looking at the handout and okay, so there's examples of solutions, and then there's question essentially. Oh, I see. There's question 4, but even question 4 has answers, right? Not solutions, but answers. And then 5 and 6, which do not. Sure, we can go over either problems similar-ish to that, or yeah. Let's talk about some examples here. Let me look at these other ones here.
I have a question.
Yeah. Yeah, someone asked about 6 as well. I'll probably do one that's similar to 6, but maybe not exactly the same as 6, just so we can not. Yeah, in fact, let's start with 6 or one similar to that. So we'll change the numbers up a little bit here. So let's write the usual things. Co-17B. Today is what, May 16th? So here's the general situation. Newton's law of cooling. Essentially says that the rate of change of the temperature of an object is proportional to the difference in the temperature of the object and the temperature of the surrounding atmosphere. So that's why, so for example, how this actually works in real life is if you wanted to say you go to the store, you buy some beverages, you want to make them cold. If you want to make them cold faster, you can put them in the freezer, because the difference in temperature between your not cold can and the freezer temperature is it's a greater difference than putting it in the fridge, right? Because maybe your fridge is at 35 degrees and your freezer is at 0 degrees. Or sorry, I'm thinking, sorry, wrong, right? Your fridge might be at like 40 degrees and your freezer might be like at 32 degrees, right? Your freezer is like, I'm Fahrenheit, not Celsius. So the bigger the difference in temperature between your object and the surroundings means that there's a faster rate of change. So that's what Newton's law of cooling says very generally, that the rate of change of the temperature is proportional to the difference in the temperature at time t and the temperature of the surroundings. And I want to point out that you don't really need this negative sign here, but that's how it's written in your problem, so we might as well include it there. That's certainly a constant. And so is that. T sub s is just the temperature of the surroundings, which we are going to generally say is a constant. So here's how we would do a problem like this. I know I have an example here somewhere. 1 second. Or do I? Maybe not. Fine. 1 second here. Okay, so for example, let's actually use the beverage as an example. So we're given a warm beverage that we'd like to be cold at a temperature of, let's say it's too hot to drink, it's a spicy 70 degrees. And we're going to put it in the freezer to cool it down as fast as possible. So we put it in the freezer with a given surrounding temperature of 32 degrees. And let's say, I'm just going to make up numbers here, so things might not come out very logically, but that's fine. The math is what we're going to do here. So we observe that 30 minutes later, the temperature of our beverage is 55 degrees. How long until the beverage is, I don't even know what temperature I would drink a beverage at. I have no idea. How long until the beverage is, let's say 40 degrees. Let's say 42 degrees. That seems like a reasonable coolness of a soda or lemonade or beer. All right, so this is a problem similar-ish to problem 6. So we're going to set this up. So all we're going to do is start off by writing this differential equation with the one constant we have already to plug in. So we're going to say that our differential equation dt, which I know is terrible, but it's kind of what we got. dt is equal to negative K times the temperature of our beverage at time T minus the surrounding temperature, which is 32 degrees. That's always how we're going to start this off. And this one other thing here, yeah. So then our job is to solve this. And then after we solve it, we will use the other information to solve for our constants, plural, because we're going to have two constants to solve for. So separate the variables. We could do this as a first order linear. I think it makes more sense as a separation of variables. I will again point out you typically don't usually have an option, but sometimes you do. In this case, you could do it either way. But I'm going to separate. If we separate, we're going to bring the capital T's to the left, the lowercase t's to the right. So I'm going to divide both sides by t minus 32 and get 1 over capital T minus 32 equal to, sorry, dt, don't forget the dt there, equal to negative k times lowercase dt. So there's our variable separated, capital T's on the left, lowercase t's on the right. Now we're going to integrate both sides. On the left-hand side, we get the natural log of the absolute value of t minus 32. On the right-hand side, we get negative kt plus another constant. Let's call it c. I know I've said a few times that you can ignore this absolute value, but I feel like I didn't do a great job of explaining why, so I'm going to do it again and explain exactly why we get to ignore it. So I will point out, you could just jump right now to say that the natural log of just parentheses t minus 32 is equal to negative kt plus c. But we're going to do it this way, and we'll talk about why we can just make that assumption here. So I'm going to try to isolate capital T. So I'm going to say that e to the natural log of the absolute value of capital T minus 32 is equal to e to the negative kt plus c. The left-hand side simplifies as just the absolute value of t minus 32. The right-hand side we can write as e to the negative kt times e to the c. What I should point out here is that the right-hand side is always positive. E to the something is always positive times e to the something is always positive. But the insides here could be negative depending on what sort of situation you have, right? It's possible that you could put something in your refrigerator that's actually colder than the refrigerator, and so the difference would be negative. Right? That's not an impossible situation to have. So how do we account for that? Well, what we're going to say is that this inside here, t minus 32, could be either plus or minus e to the c times e to the negative kt. And then what we do is we go ahead and say, well, look, this plus or minus e to the c, we're just going to call that, I like to call it a, other people like to call it c, I'm going to call it a. And then we're just going to say to ourselves, a could either be positive or negative as necessary. So really, we're going to do all this, but what I would strongly encourage you all to do in the future is don't do this. Instead, just start with this and then do e to the that equals e to the that. So then t minus 32 equals e to the negative kt times e to the c, and then just say that e to the c is a. You still get to the same place without having to think about the fact that there's an absolute value thing going on. And it's totally valid, right? You're not ignoring the absolute value, you're just saying, I know that it's going to work out fine if I just don't write that in there. So it's totally fine to do it. I just always feel like I have to convince myself every time that, oh yeah, we're doing an okay thing. So that's what's happening there. And then I would probably isolate t, although I don't think it's super necessary. And then I'm getting that t equals 32 plus a times e to the negative kt. Yeah. And I would actually point out, no, so some other classes do kind of just jump straight to this and say, like, if you have this Newton's law of cooling, it's always going to be the case that your temperature at time t is equal to your surrounding temperature plus a e to the negative kt, and then we can solve for a and k. So we're going to use this general solution to then solve for our constants a and k. So I'm going to use more paper here because I made a personal choice to try not to squeeze everything into little corners here. So we've got our general solution, t as a function of little t is equal to 32 plus a e to the negative kt. And we also have some data points. We know that at the beginning, the temperature, let's use little t here, sorry. Capital T here. At time equals 0, the beginning of this process, the temperature of our beverage was, I don't remember what it was. We said it was, I think, 70 degrees. And then we said 30 minutes later, so we're deciding to measure time in minutes. The temperature of our beverage was 55 degrees. And then the question that we're going to try to answer here is, what time is it when the temperature of our beverage is 42 degrees? A little more space here, sorry. This camera always feels like it's like off center. Like I feel like I'm like way to the left of where the camera should be focusing, but not. So start with plugging in 0. T of 0 should equal 70, but that's going to equal 32 plus a e to the negative k times 0. So then using this equation here, 70 minus 32 equals a times e to the 0 is just a. So a is going to be 38. Plug that back into our model. So now the temperature at time t is 32 plus 38 times e to the negative kt. And we can see that if you plug in t equals 0, you're going to get 32 plus 38, which is 70, as we should. And then we're going to plug in the other data point. So I'm going to say that temperature at 30 minutes later is equal to 55. And that should equal 32 plus 38 times e to the negative k times 30. And then we're going to solve for k. K is usually not going to be very lovely to find, but it's fine. 55 minus 32 is 23 equal to 38 e to the negative 30k. Divide by 38. Take the natural log of both sides, and natural log of 23 over 38 equals just negative 30k. So then we end up getting that k is equal to the natural log of 23 over 38 divided by negative 30. Which I would point out is a positive number. Natural log of 23 over 38 is the natural log of a number that's less than 1. So it's negative, and then that negative number divided by negative 30 is positive. I don't think it really matters, though. I mean, it matters, I guess. But so then if we plug this back in, I really think it's kind of silly to write. Well, I'm going to write it, but I'll tell you why it's silly. I think it's silly to write that T of t is equal to 32 plus 38 e to the negative natural log of 23 over 38 over negative 30 times t. Those negatives definitely cancel out. So I would rewrite this as the temperature at time t is equal to 32 plus 38 e to the natural log of 23 over 38 all over 30 times t. Let me ask a good question here. Well, maybe two. What I think might be a good question. At time equals 0, the temperature is going to be 70 degrees. As time goes on, is this object getting colder or warmer? Is this temperature getting larger or smaller? Well, I mean, we can look over here. As time goes on, it seems like the temperature is getting colder, which means that this numerical value up here, this natural log, I know it's kind of messy there, this natural log of 23/38 over 30, that should be a negative number. Because if this value is going to get smaller, you have to have e to the something that's getting more and more negative so that the output's getting smaller and smaller and smaller. And it is, because again, 23 over 38 is less than 1, and the natural log of a number less than 1 is negative. It's not required that you see this, it's just good to make note of so that you're like, oh yeah, things seem like they're making sense. So then finally, yep, let's use all the paper today, sure. So then finally, to answer the question, we're going to set the temperature equal to 42, and then we're going to set that equal to the actual formula, And then we're going to solve for time, which is a very similar process to solving for k, which we just did. So subtract 32, you get 10 equal to 38 times e to the, writing this is terrible, e to the natural log of 23 over 38 over 30 times t. Divide by 38. If I were really doing, I might, like, if I were doing this as a student, I might just write k every time instead of writing the actual number, and then at the very end, write in what k actually was. So I didn't have to write the natural log of 23 over 38 over 30 like 5 times. Take the natural log of both sides, so the natural log of 10 over 38 is equal to the natural log of e to the stuff is just the stuff, plus the natural log of 23 over 38 divided by 30 times t. And then we multiply both sides by the reciprocal of this, so that t is equal to 30 times the natural log of 10/38 over natural log of 23/38. And then I have a calculator. No, I don't have a calculator. I can try to use my phone, but that seems ridiculous. Let's just use the computer here. If we use a calculator here to calculate 30 times the natural log of 10/38 divided by the natural log of 23/38, we get a value that's about way too long to wait for your, drink to get cold. It's approximately, it's not too long. Sorry, I was thinking it was hours for a second. So this is approximately 79.76 minutes. Probably not a realistic actual like situation because I just made up the numbers, but not like an infinite amount of time. So okay. So that's how you approach a problem like this with the Newton's law of cooling, where you are really, I mean, I say more generally, this is how we approach most differential equations. We start off with the differential equation, and then we either separate or use a first order linear. Usually you only have one choice. Here, I will again mention you could have done it either way. So then, right, you solve it, and then you have to solve your constants. Are there questions about any of the things I've done here? Okay. Let's look at some more examples. So I would say for a lot of these problems, especially these word problems, the setup is really the hard part. Not that solving it also isn't challenging, but setting it up is really kind of where I often have to really think the hardest. Let's look at, yeah, I want to look at this tank problem here. This is the tank problem from his worksheet 2, which I think is worth, yeah, let's look at this third one here. This is worksheet 2, number 3. If there are other problems you would like me to address, I'm certainly happy to. I'm just kind of picking and choosing things that I think are important to see. So here's the setup. A large tank holds 100 gallons of fluid in which 10 pounds of salt is dissolved. I feel like it was the same beginning, previous one we did. A mixture containing a ½ pound of salt per gallon, or I would say a mixture with a concentration of a ½ pound of salt per gallon. Words. Flows into the tank at a rate of 6 gallons per minute. The well-stirred mixture flows out of the tank at a rate of 4 gallons per minute. So interesting. So the first question here is, how many gallons of solution are in the tank after 4 minutes? After 10 minutes, sorry. Which I feel like is not a typical kind of first question for a question like this. Usually we're like, set up the differential equation. So that doesn't seem like a terrible question to ask, right? How many gallons of solution are in the tank after 10 minutes? Well, we're putting in 6 gallons per minute. I don't feel like I like this question. I'm curious what he's getting at here. Sorry, apologies. I picked this question, I know, but I wanted to see one thing. I feel like this question is, I'm just curious what he means by this. He didn't post solutions to it. Okay, fine. We'll live. Sorry. Yeah, okay. How do you read this question? Like, I feel like what it means is just how many solutions have, of how many gallons of the solution have we added into the tank? But I don't know. To me, this doesn't seem like, I don't like this question. I apologize. I like the setup here. I don't think this question's good because, like, what are we taking into account? Are we just thinking about the solution that's been added, or was thinking about the fact that we are draining the tank as well? Oh, no, I'm dumb. Okay, I figured it out. So the solution, just the whole thing, not the stuff we're adding. How much, the better, a way that I could have phrased this that would have made more sense to me is, how much volume is in the tank after 10 minutes? So we started off with 100 gallons. Time equals 0. Volume is 100 gallons. 1 minute later, we've added 6 gallons and we've also drained 4 gallons. So 1 minute later, we've added a net of how many gallons? Show me on your fingers. How many gallons have we added after 1 minute? Thank you. Yes, that many. So in 1 minute, we've got to 102 gallons. And every minute, we're going to add another 2 gallons. So after 10 minutes, the volume should be 120 gallons. And after 1 hour, which is 60 minutes, we should have added 120 gallons to our 100 gallons. So our volume should be 220 gallons. But more generally, at any time t, the volume in the tank should be 100 gallons plus 2 times t, where t is the number of minutes that have passed. Cool. Where did I get the 2 gallons? So I got the 2 gallons by saying that that this mixture flows into the tank at a rate of 6 gallons per minute. And the well-stirred mixture flows out of the tank at a rate of 4 gallons per minute. So every minute we're adding 6 gallons and taking out 4 gallons for a net increase of 2 gallons per minute. That's where we're getting the 2 gallons from. Okay. So a harder question to answer, I think. I thought the last one was hard, but then I figured it out. So let's see. So here's question B. How much salt is in the tank after 10 minutes? And I don't feel like this is we can just figure it out. This, to me, this is we have to solve for S of t. So we need to write and solve the differential equation for salt as a function of time to be able to answer this question, which is challenging. It's not like unreasonable, like it's not out of your realm of possibilities. It's harder than most differential equations we encounter. And we'll see about how much we want to do here because, well, I definitely want to set it up. We'll see if we want to solve it. All right, so for any tank problem, it's always the rate of change of your stuff, in this case of our salt. So the rate of change of the amount of salt is equal to the amount in minus the amount out. I really should say the amount in per unit of time. In this case, I think it's per minute. Yeah, per minute. And the amount out per minute. So that's going to translate mathematically to ds dt. Actually, let me back it up for 1 second. Let's say, just so we're all clear, we're going to say that S of t is the amount, not the concentration, the amount of salt in the tank at time t. So then ds dt is the rate of change of the amount of salt at time t. And the amount in, well, how much salt are we putting in? We go back and read the question. We're putting in a mixture containing ½ pound of salt per gallon. So a ½ pound of salt per gallon. And we're putting it at a rate of 6 gallons per minute. The rate or the amount that's going out of the tank, well, this is the part that's always challenging, I think. Or I should say, this is the most challenging part of the setup, is the concentration that's going out. So the concentration that's going out is the amount of salt in the tank, which is S of t, the amount of salt in the tank at time t, divided by the volume of the tank. And in this case, the volume of the tank is not constant. We just did it in the previous problem, right? The volume of the tank is 100 plus 2t. So there's your concentration out, and that also is in pounds per gallon. And then the rate that it's going out is 4 gallons per minute. I think it's good to write the units here so that you can see that the units are actually going to make sense, right? If we cancel the units here, the gallons here and the gallons here cancel to get half a pound times 6, so 3 pounds per minute. So we're adding in 3 pounds of salt every minute, and we're taking out S of t times 4 over 100 plus 2t. I'm gonna write that as 4 times S over 100 plus 2t pounds of salt per minute. That's how much salt we're taking out every minute. So there's our differential equation, which without the units looks like ds dt equal to 3 minus 4s over 100 plus 2t. And this is definitely a case. So I know for the previous tank problem, I think I mentioned that you could, like we did on class on Tuesday, I mentioned that you could either solve it using first order linear or separation of variables. I think we did first order linear. This one, where the volume is changing, you do not have a choice. It's definitely always going to be first order linear. We cannot separate variables here. Because if we want to separate variables, you'd have to try to like get one fraction here, and then you'd have a numerator with t's and s's added together, and that would be problematic. So this one you cannot separate. So we'll solve it the other way. So to solve it the other way, to do it as a first order linear differential equation, we have to write it in the standard way. meaning it's got to look like ds dt, or if you prefer s prime, plus some function of t times s equal to some other function of t. So to me, it looks like I have to bring this 4s over 100 plus 2t over to the left-hand side. So I'm going to write this as ds dt plus, and I'm going to pull the s off to the side. I'm going to write that as 4 over 100 plus 2t times s equal to the remaining stuff over there, which is 3. And that looks good. I mean, you know, compared to, it looks good as far as what we have to deal with. All right, so we have our differential equation. It's written in the right format. Now we have to do the integrating factor thing. So our integrating factor here, mu of t, is going to be e to the integral of that p of t right there, 4 over 100 plus 2t dt. We could probably make that slightly simpler. 4 over 100 plus 2t, there are definitely, we could cancel the 2, right? We could write that as e to the integral of 2 over 50 plus t, just dividing the top and bottom by 2, which will actually make integrating it a tiny bit easier. So this is going to end up being e to the, let's see, the integral of 2 over 50 plus t is 2 times the natural log of 50 plus t. Whereas just to point this out, here, if you did it this way, you get e to the 4 times the natural log of 100 plus 2t, but then you have to divide by 2, which is just a little bit more annoying. So this is a better way to go here. And then we always want to simplify this as much as possible. Specifically, if you have an e to the something with a natural log in it, you always should take this coefficient, whatever it is, bring it up as the power of the argument of the logarithm, and then write this as e to the natural log of 50 plus t squared, which is then just 50 plus t squared. We always want to do that if there's a log up there. If there's not a log up there, then you're kind of stuck with what you have. Okay, we're going to multiply everything by this. So we have that equation here. Multiply everything by mu of t. So we get that ds dt times 50 plus t squared plus 4 over 100 plus 2t times 50 plus t squared times s is equal to 3 times 50 plus t squared. Here's the good news. You don't have to actually be able to see that this is the derivative of a product. It always will be. We are 100% assured that this left-hand side here has to be the derivative of s times our integrating factor. If I've been thinking slightly more ahead, I would have written this ds dt as s prime, and then said the thing I usually say, which is that wherever your prime is, just take that s prime times your thing and move the prime to the outside of the parentheses. It's not like real math, but it works. Then we're going to anti-differentiate both sides. We're almost there. I know this is a long problem, but we're almost there. So we're going to say that s times our 50 plus t squared is equal to the antiderivative of, let's pull the 3 out in front, 50 plus t squared dt. This is not terrible to integrate, right? It's going to be 3 times the antiderivative of 50 plus t squared is going to be 50 plus t cubed divided by 3 plus c. And oh, look, the 3's even cancel. How nice is that? Then we have that s times 50 plus t squared is equal to 50 plus t cubed plus c. And now here's the really important part whenever you solve a first order linear differential equation, when you divide both sides by your integrating factor, the c has to get divided by the integrating factor. So solving this here, we have s equal to 50 plus t cubed divided by 50 plus t squared. Yes, I'm going to simplify that. plus C divided by 50 plus T squared. Or written more nicely, S as a function of T is equal to 50 plus T plus C over 50 plus T squared. Whoops, that was terrible. Sorry. Sorry, I don't mean to be so slightly there. For a problem where you're representing a real physical situation, there should be an initial condition, right? Like there was an initial condition in this problem. They didn't specifically say your initial condition is this, but they certainly wrote the words, a large tank holds 100 gallons of fluid in which 10 pounds of salt is dissolved. So we know that at time equals 0, the amount of salt is 10 pounds of salt. So we're going to plug in this initial condition to get what the constant C is. So we're going to say, great, 10, the amount of salt, is equal to 50 plus 0 plus C divided by 50 plus 0 squared. And then we're going to solve for C. It's going to be not super lovely. The 10 minus 50 is negative 40 equal to C over 50 squared is 2,500. So this C value is going to be quite large. It's going to be, let's see, 4 times 2,500 is too much for me to think about 10,000, 100,000. So C is negative 100,000. Okay, fine. It's weird, but fine. So our solution to this differential equation is the amount of salt is 50 plus T plus 100,000. Sorry, negative 100,000 divided by 50 plus T squared. Kind of gross, but totally fine. And now finally, after all that, we can answer the seemingly innocuous question of how much salt will be in the tank after 10 minutes, which I feel like is not even, it's barely worth answering in my opinion. But if we want to find the amount of salt after 10 minutes, so I keep trying to line things up here so it's not quite so terrible. The amount of salt after 10 minutes is just S of 10, which is going to be 50 plus 10. I'm going to write minus 100,000 over 50 plus 10 squared. So some terrible number. 60 minus 100,000 over 3,600. Whatever that happens to be. I guess we could calculate it. I do, normally I don't like think it's super important to get a decimal approximation, but when you're talking about physical situations like this, where you might actually like to know what the answer kind of sensibly meant, if we actually do this and get 100,000 divided by 36, why am I doing that? It's 1,000 divided by 36, which should be close to 30. It's 27.77. So this is going to approximately equal 60 minus 27.77, which is approximately 32.23. So the amount of salt after 10 minutes is about 32 pounds. And after an hour, same sort of deal. S of 60 would be 50 plus 60 minus 100,000 divided by 50 plus 60, which is 110 squared. So the same sort of idea there. That would be approximately 110 minus 100,000 over 110 squared is what, 121,000? That's going to be pretty close to 110 because 100,000 divided by 120,000 is just a little bit less than 1. So this is probably like 108 point something pounds of salt. So tank problems, they're kind of gross, but they're always a process. I feel like we should do one more that's not so I think personally, usually we don't end up having to do the ones where the amount of volume going in is different than the amount of volume going out. Like we just did. I feel like that's pretty atypical. let's do one more. And I know last time we solved it doing first order linear. Let's do one more tank problem, but let's solve it doing it the other way using separation of variables. So that you know that you have options. Are options good? Maybe, I don't know. Sometimes it's better not to have any choices. You're like, I just have to do it this way, but we'll do one more without options. Yeah, I don't love you. You know what? I can just make up a tank problem. So let's say we have a tank that holds 200 liters of solution. With 20, sure, 20 kilograms of sugar dissolved into it. We're going to add a solution concentrated at, let's say, a third of a pound, not pound, a third of a kilogram of sugar per liter at a rate of 5 liters per minute. And then we're going to drain the tank. Yes. Yeah, of course. Better? Okay. Drain the tank at the same rate. And then we'll ask a question like, so if this is all anyone wrote, you'd be like, well, they're not asking me to do anything, so we should ask a question. So how long until the tank I don't like this one, has, let's see, has 50 kilograms of sugar in it. An alternative way I could have phrased the same question, how long until the concentration of sugar in the tank is a quarter of a kilogram per liter? Right, because if the tank is 200 liters and it had a concentration of a quarter of a kilogram per liter, a quarter of 200 liters is 50 kilograms. So, or it's 50, well, a quarter of 200 is 50. I'll say that. So I want you all to set it up. So set up the differential equation. So set up your rate of change of sugar equal to the amount in per minute minus the amount out per minute. I'll give you a minute and a half to do that. All right. And when you say you're going to give people time, you should start actually keeping track of the time. big, that's close to the amount of time I said it was gonna be. So. Our differential equation, ds dt. The amount in almost always is a constant. Right? Usually there's a way to set this up so the amount in is variable. Here the amount in is, we're putting in a concentration of 1/3 of a kilogram per liter at a pace of 5 liters per minute, which is going to simplify it to 5/3. We're taking it out at a concentration of however much sugar is in the tank divided by the volume of the tank, which is not changing. If you like, I should say S kilograms, right? The amount of sugar in kilograms divided by the volume of the tank in liters. Multiplied by the rate at which we're taking it out, which is 5 liters per minute. And then I don't think you need to write the units here, but I like to write them because it helps me kind of it helps me make sure I'm doing the right thing. I can look at this and say, okay, my dsdt here is, I'm putting in 5/3, and it is kilograms per minute because the liters cancel. And I'm taking out S times 5 over 200. And again, it is kilograms per minute because the liters cancel. Let's simplify that down to S over 40. And even though I probably would prefer to solve this as a first order linear, let's solve it as a separable differential equation. So we're going to do it as a separable one. I will again say, just as a reminder, usually you don't have a choice. Usually it's either going to obviously be only first order or only separable, but for some of these we do happen to have options. So here, if I'm thinking of it as separable, I have to essentially divide both sides by this whole entire quantity, 5/3 minus S over 40. Now I think that's kind of terrible. We can make it a little bit better if we get a common denominator on the right-hand side before we do that. So let's say that ds dt is equal to, so I multiply this by 40 over 40, it's going to be 200 over 120. Multiply this by 5. I guess I didn't need to get rid of that. I didn't need to reduce that fraction. Oh well. No, yes, I did. I'm saying crazy things there. Sorry about that. Make sure your 5 and your S don't look too similar. So that's an S. It might be good to write S of t if you're concerned. Multiply this by 3 over 3 and get 3 times S over 120, which we're then going to write as ds dt equals 200 minus 3s. And instead of saying divided by 120, let's say times 1 over 120. Now it's a little bit less terrible to divide both sides by 200 minus 3s. So we're going to say that 1 over 200 minus 3s ds is equal to 1 over 120 dt. Yeah, I definitely think I come down on the side of using first order linear if you have a choice, because it's usually, even though the process might feel slightly more complicated, usually the algebraic manipulation is less complicated for a first order linear. So that's probably what I would recommend in general, if you have a choice, which you usually won't. So then we're going to anti-differentiate both sides. On the left-hand side, we're going to get the natural log of the absolute value of 200 minus 3s. Because I'm not going to write the absolute values because I don't need to, even though I really, really feel like I should. What do I need to divide by here? Sure, that's a yes. Multiply by negative 1/3 or divide by negative 3. Either way you want to say it. On the right-hand side, we're going to get 1 over 120 times t plus a constant. And now our job is to solve for s. Yeah. Yes, exactly. From the negative 3s. We're dividing by the coefficient of our variable. And again, right, just as a reminder, if we took the derivative of the natural log of 200 minus 3s, we would get 1 over the stuff multiplied by the derivative of the stuff. And the derivative of the 200 minus 3s is exactly negative 3, which will cancel out the negative 1/3, which will give us back that. So then solving this, we're going to multiply both sides by negative 3. So check this out. We're going to get the natural log of 200 minus 3s equal to negative 3 times 1 over 120, which we can reduce in the next step. And negative 3 times a constant, still a constant. And that's, I don't love doing that, but it's what everyone's going to do. So that's what you should get used to seeing. So then we e both sides, we get e to the natural log of 200 minus 3s equal to e to the, let's simplify that as negative 1 over 40 times t plus c. And then that's going to become natural, sorry, not natural log, just the 200 minus s, minus 3s, sorry. 200 minus 3s equal to, we're going to write the right-hand side as e to the negative 1 over 40t times e to the c, which is then going to become an a, or whatever letter you prefer to choose. Okay, we're almost done. We have 200 minus 3s equal to a e to the negative 1 over 40 times t. We're solving for s. We have, I really like to do this, but I don't want to like divide by -3. I really like, I hate dividing by a negative number. I just don't know why. It's just like I have a personal bias against it. So I'm going to choose to say 200 minus a e to the negative 1 over 40t equals positive 3s. And then divide by 3. I know it seems silly, but it's just, I don't know. It's what I do. So S of t is 1/3 times 200 minus a e to the negative 1 over 40t. And then we're going to use our initial condition to figure out what a should be. So our initial condition was that at the very beginning, the tank had, I think I said 20 kilograms of salt in it, or sorry, sugar in it. Let's double check before we just say what we think it is. Somewhere over here, let's see. In the beginning, yes, we had 20 kilograms of sugar in the tank. So that means that S of 0 is equal to 1/3 times 200 minus a e to the negative 1 over 40 times 0. And that should equal 20. So something to see here is that I probably waited too long to solve for a. Not like it's super hard to solve for a here, but there was a better moment to actually solve for my initial condition. If I had gone back like maybe, I don't know, like right here, that might have actually been the better moment to solve for a. Because if we'd done it there, we would have gotten 200 minus 3 times 20 equal to a times e to the 0. And then you get a equal to 140. Whereas doing it here, I have to do more work, right? I have to like multiply both sides by 3 and say 200 minus a equals 60, and then 200 minus 60 equals a. So you get the same thing, and it's not like it's a lot more work, but sometimes it is, I'm sorry. So I would say if you can kind of pick your moment to find your constant, there often is a best moment where it's going to be the least amount of work. Again, not super terrible to do it when we did it at the end, but if I had done it right here, it's even easier. And then we would write our final function for the amount of sugar at time t as equal to 1/3 times 200 minus 140 e to the negative 1 over 40 t. And then finally, to answer the question that was asked, which is how long until there are 50 kilograms of salt in the tank? If I can move this piece of paper at all. So to find how long it takes to get to 50 kilograms of salt in the tank, we're going to set S equal to 50. So we're going to have 50 equal to 1/3 times 200 minus 140 e to the negative 1 over 40 t. And then we're going to solve for t. So multiply both sides by 3. Subtract 200, so negative 50 equals negative 140 e to the negative 1 over 40 t. Divide both sides by negative 140, so you get 50 over 140, or 5 over 14, equal to e to the negative 1 over 40 times t. Take the natural log of both sides. The natural log of 5 over 14 equals negative 1 over 40 times t. And finally, multiply both sides by negative 40. to get negative 40 times the natural log of 5/14 equal to t. Okay, let me ask you all, does our answer make sense? Let me ask you a different question. Is our value for time positive or negative? It's not negative. It's positive. I know there's a negative out there, but so everybody, as a reminder, here's the graph of y equal to the natural log of x that has an x-intercept at 1. So if your input is less than 1, like right in here, your output is definitely negative. So this natural log of 5/14, I don't know what number that is, but I know for sure that it's a negative number. So that negative 40 times that negative number gives you a positive time. So sometimes we have to ask ourselves, does this answer make sense? And it might look like it doesn't, but it actually does. So just be a little extra careful here. If you wanted to, you could rewrite this as positive 40 times the natural log of 14/5. Which is kind of annoying, but perfectly valid answer. Okay, one more question, and I like this question. I feel like Adele likes this question too, even though I haven't seen him ask it, but I feel like he is. What, or I should say, if we let this process run indefinitely, or forever, how much sugar will we have in the tank? Which is just kind of a long-winded way of saying, what's the limit as t goes to infinity of this solution to the differential equation? So we take the limit as t goes to infinity of our expression, which was 1/3 times 200 minus 140 e to the negative 1/40t. Okay, help me out. As t goes to infinity, what happens to e to the negative 1/40 times t? Is that getting big? Is that getting small? Well, are we getting e to the infinity or e to the negative infinity? Point to the left if you think it's negative infinity, point to the right if you think it's positive infinity. So we're getting e to the negative 1/40 times t. We're going to e to the negative infinity. Because we're jamming in a really, really big positive number for t, but then we're multiplying it by negative 1/40. So it's becoming super duper duper negative. And if you think about the graph of e to the x, e to the very, very negative infinity is going to be super duper close to 0, right? The graph of e to the x looks like that. So if x is going to infinity out that way, then e to the x is really big. If x is going to negative infinity out that way, then e to the x is really, really close to 0. So this e to the negative 1/40t goes to 0 as t goes to infinity, which means we're left with 1/3 times 200, which is approximately 66.66, whatever. And then, as I said previously, the interesting thing to me is that the concentration of the tank of the sugar in the tank is going to be exactly 1/3 of a kilogram per liter. So the concentration, the limiting concentration here is exactly the limiting amount of salt, 200 thirds of a kilogram, divided by the volume, which is 200 liters. The 200s cancel and you get exactly 1/3 of a kilogram per liter. And it is not at all a coincidence that that is the concentration of the thing that we're adding to the tank. Again, I find this interesting. I think it could, I would certainly ask this question on a test if I were giving a test, but I'm not the one writing the test, so who knows. But I think it's a question that is a thoughtful question. So There you go. Question. So you can do it either way. So I'm thinking of it as e to the x and then letting x go to negative infinity. Alternatively, you could think of it as y equal to e to the negative x, which looks like this. But then you're letting x go to infinity. So you're still getting closer and closer to 0. Either way is fine as long as it's right. Cool. All right, have you had enough tank problems yet? I mean, you can say no, we can do more. The thing is, they don't really get that much different. They're just, it's the same kind of thing every time. You have a differential equation, you have the amount of stuff going in, the amount of stuff going out, and the amount of stuff going out, the concentration is typically going to be the amount of salt divided by the volume of your tank, whether that's typically, which will be constant, not always. And then it's the same sort of process every time. What time is it? Oh, the time is flat. I'm like, it's already 10. I was like, I feel like I have like good, 25 minutes. Nope, I have 13 minutes. Okay. Are there any other pressing differential equations questions? Which I'm really, really happy to address. If I see anything that's pressing here. Sometimes things are just super funky. If not, we can move on to the next one. You guys like no? Oh, you guys have a quiz today, right? Yeah, I mean it's Thursday. You always have a quiz unless there's a test. And the quiz was like all differential equations, right? That's what he said in his email or whatever. Like it's just all like everything differential equations. So let me say a couple things. You're certainly welcome to ask questions if you want to. I would imagine you'd probably get asked something about stability or instability. So let's talk about that for 1 second. But again, if you have a question, don't hesitate. So let's say we're given the differential equation dn dt is equal to 4 minus n times n minus 1 cubed times n to the 7th power. Usual question. Find all the equilibria and classify them. Find and classify equilibria. Finding them at least if it's already factored, it should not be terrible. Sometimes it might be more work. So here we're going to set our differential equation for what it's equal to 0, and we're going to get 3 critical points or 3 equilibria. N equal to positive 4, n equal to positive 1, n equal to 0. We could do that. So then, how to classify? I'm a fan of the graphical method. Let's do that first. Especially here, the other methods would probably be kind of terrible, but we can talk about it. So if I was going to classify these, I would draw the graph. My horizontal axis is n, my vertical axis is dn dt. I'm going to plot my 3 values, 0, 1, 4. And then I'm going to try to see what's going on. Why do I feel like I keep getting out of focus here? Yeah. So start wherever you like. I personally like to start as far right as I need to. So pick a number larger than 4. Actually, don't. Just pretend like you are. Say, okay, something bigger than 4. What's 4 minus something bigger than 4? Is it positive or negative? How about 4? How about something bigger than 4 minus 1? How about something bigger than 4? So it's a negative times a positive a negative times a positive times a positive. So over here in the bigger than 4 area, it's going to be negative, meaning we're under the axis. Here's why I said don't pick a number. Because if this had been, instead of being 4, if this had been the letter A, and we knew that A was bigger than 1, and we said pick something bigger than A, well then A minus something bigger than A is negative. A minus something bigger than A minus 1 is positive because we know that A is bigger than 1, and A is positive because we know it's bigger than 1. So here's what I'm saying. I'm saying because I wouldn't be surprised if we did an example where you didn't have actual numbers. So I'm saying like, instead of having this, what if we had instead a minus n times n minus 1 cubed times n to the 7th, and we were given that a was greater than 1. So then instead of having a 4 there, we would have an a. And I'm saying, well, now it's hard to pick an actual number. If you want, you can pick 2a. That'll work because 2a is bigger than a if a is already positive. But really, you should just say, I'm picking a number larger than a. So and I'm plugging it in for n. So a minus a number bigger than a, negative. A minus 1, well, since a is larger than 1, positive. A to the 7th, well, a is already bigger than 1, so that's also positive. So in a similar way, you can say to yourself, oh, this product is going to be negative. I think that's useful. And then between 1 and 4, well, here's where I don't think you should keep picking values. I think you should say to yourself, 4 came from this factor, which is raised to an odd power, which means we cross the horizontal axis. Similarly, 1 came from this factor with an odd power, which means we're going to cross again over here. And 0 came from this factor, also with an odd power, which means we're going to cross here. If all is good and right with the world, all your powers will be odd, because you'll cross every time. So then we know that these are what's happening with d and dt. So if d and dt is positive, n is moving to the right. It's getting bigger. If d and dt is negative down here, n is moving to the left because it's getting smaller. D and dt is positive, n is moving to the right. D and dt is negative, n is moving to the left. So, question. Oh, because if I pick a number bigger than a, right? So let's go back over here. For 4 minus n, I picked a number bigger than 4, like 5. 4 minus 5 is negative. So a number minus a number that's bigger than it is going to turn out to be negative. So here, if I'm plugging in a number larger than a for n. So a minus a number that's bigger than a is going to be negative. Right, exactly. We have to plug in for n. Because a is the constant and n is the variable. So show me on your fingers how many of these are stable. I have to look now. Yeah. Yep. 2 are stable, and by process of elimination, 1 of them is unstable. Specifically, n, I would probably write n hat. You don't have to, but n hat equal to 1 is unstable, and n hat equal to 0, and n hat equal to 4 is stable. Okay. Understanding check. If we said that we were given that n of 0, meaning n at t equal to 0, was equal to 3, what is the limit as t goes to infinity of n of t? Watch, I'll take a minute to think about it. Show me on your fingers. I think I'm seeing the right number of fingers. Yeah, I see a couple. I see a couple 4s, which is the right answer here. So how do we know it's 4? Well, if you're starting at time equals 0, right here at n of 0 equal to 3, well, if we start at n equal to 3, then as time moves forward, we're going to get pushed to the right towards that stable equilibrium, which is 4. Someone asked a question, how would we write this in interval form? I'm not sure what you mean exactly, like in interval form. I guess I don't know what we would like. You could specify where d and dt is positive or negative, but I don't exactly know why we would be needing to do that. I feel like, was there a question in the back row? Okay, I thought so. For the stability and instability. I don't exactly know, like, is that something? I'm not sure. I'm talking about stability and instability. I'm saying that n hat equal to 1 is unstable, and n hat equal to 0 and n hat equal to 4 are both stable. But I don't know about talking about, like, sure, if you asked where n was increasing or decreasing, so yeah, if someone said if we asked about where n is increasing or decreasing, definitely we can say that n is increasing. Can you see that? No, you cannot. N is increasing on the intervals where d and dt is positive. So it'd be increasing from on the interval from negative infinity to 0 and from 1 to 4. Similarly, we could say that n is decreasing where the derivative is negative. So from 0 to 1, union 4 to infinity. Hopefully that answers the question. Could we do an example with constants a and b? Sure. Yeah. What time is it? Yeah. Yeah, let's see. Let's see if I can make something up that makes sense. Let's say we're given this dy dt equal to, sure. Yeah, that's going to be terrible. Y minus a cubed times y minus 1 times, yeah, let's hope here, b over a minus y, where 1 is less than a is less than b. That gonna work out all right? Yeah, that should work out okay. Okay. Find and classify. So finding them, again, hopefully it's already factored for you. If not, you have to do the factoring, but it can't be super complicated. So our equilibria here are going to be y equal to a, y equal to 1, and y equal to b divided by a. Yeah, but I think that's unfortunate. Yeah, is that true? Yeah, I think I've unfortunately. So the problem here is that I don't know what's bigger, a or b over a. Right? There isn't, like, I don't know how much bigger b is than a. So let's say, I'm going to say one more thing. I'm going to say that b is less than a squared. This is a complicated setup. No doubt about it. So here's the equilibria. We're going to plot them on, I still think the graphical method is better here because multiplying this out to take the derivative, just a little too much. Like, we could do it, but it's probably not what's intended with a problem like this. So let's try and do it the graphical way. We got a minute, we can make this happen. So 1 is the smallest of these three things. A is bigger than 1. And since b is bigger than a, if b is bigger than a, then b divided by a is bigger than a divided by a, which is 1. So b divided by a is certainly bigger than 1 as well. So 1's the smallest. What's the next smallest? Well, let's find out. We know that b is less than a squared. So if I divide both sides by a, because I'm trying to see what b divided by a is, b divided by a is smaller than a squared divided by a. So b divided by a is smaller than a. So b divided by a, which is still bigger than 1, is the next thing. And finally, the biggest thing is a. So if you're given constants like this, you have to have a way of figuring out which one is the largest, smallest, etc. Here is where I especially think starting all the way to the right is a good choice. So let's pick a number bigger than a. Bigger than A, bigger than A, yeah, bigger than A. We can pick B if we wanted to. B minus A, positive. B minus 1, positive. Ooh, B over A minus B. Good question. B over A minus B. Let's factor. A is bigger than 1. So 1 over A is smaller than 1. So 1 over A minus 1 is negative. So if we pick y equal to b, we have a positive thing here, a positive thing here, and a negative thing here. The overall sign is negative. And then we shouldn't pick anything else. We should just say a came from this factor, which is raised to an odd power, so we change. B over A came from this factor, which is raised to an odd power, so we change. And 1 came from this factor, which is an odd power, so we change. I suppose we could have picked an easier thing to do here, which I just noticed because I'm sometimes a little slow, is if I picked y equal to 1/2, that might have been easier. Maybe, I don't know. 1/2 minus A is certainly negative because 1/2 is smaller than A. 1/2 minus 1 is certainly negative, obviously. And B over A minus 1/2, well, B over A, I don't know, it's not clear. It's not clear to me that B over A is bigger than or smaller than 1/2. So I feel like it's probably not the right choice. I think we made the best choice we could. And then usual deal, increasing, decreasing, right, like that. So we have a stable equilibria at 1 and A, unstable at B over A. And I should stop talking because it's 10:23. Good luck on your quiz today. Have a nice weekend. See you all on Tuesday, where we'll start talking about 3D graphing stuff and vectors. And I have office hours over in CADS starting in a little bit.